Okay, good. Thank you very much. First, thanks to the organizers for the invitation. Right, it's my first time here. Actually, I was supposed to come 4 years ago. I could not because I have a back issue. I'm glad I could come here. Right, so I would like to discuss quantum grassmannians as roots of unity. But I will start with quite a longish introduction on why I'm interested in doing some computations, basically in this case. So basically, this is a story that started with total positivity and a link we established between totally non-negative grassmannian and quantum grassmannian. And on the totally positive side, the physicists are very interested in some combinatorial objects constructed from the totally non-negative grassmannian. So I won't go as far as defining this object, but I will try to give you the hint on where they are going and what kind of objects they are interested in, and try to motivate the kind of computation we are doing on the quantum side, possibly to solve some problems on the physics side later on. Right. Okay, so I will start very slowly. It's still early. So I will take matrices with real entries, and I will say that the matrix is totally positive if all of its minors of all sizes, in particular the entries, are positive, and the matrix is totally non-negative if all of its minors are non-negative. Okay, so that's a very easy definition. And you can look at plenty of examples. So if you look at this, you can probably convince yourself that this matrix is totally positive. Okay. Determinants, minors are linked to short determinants. This one is not totally positive. It has 0 entries, so 1 by 1 minors that are 0. So it is totally non-negative, and I'm hoping you see some pattern here again. This one lacks pattern, but if you're getting bored with my talk, you can probably try to check that this is a totally non-negative matrix. It will take a bit of time, but it's doable. How much time will that take? Well, you need to have an idea of how much minors you need to compute. So if you have a 4 by 4 matrix, you can try to count the number of minors you can form on a 4 by 4 matrix, and there are 69 of them. In general, for an n by n matrix, you have the number of minors is given by this formula. This actually, the square of the n choose k is actually the number of k by k minors in an n by n matrix. Why? Because to form a k by k minor, you need to select k rows out of n and k columns out of n. That gives you the number of minors. It's a first year exercise to prove that this identity, and then you can use Stirling approximation of the factorial to obtain that actually the number of minors is growing exponentially with n, with the size of the matrix. Right. So this is bad news. It's a very easy concept a priori to test whether a large matrix is totally non-negative or totally positive. You have in front of you a computationally difficult problem. But there are solutions to this, which I'm not going to discuss at all today. What I would like to discuss is the composition of the space of totally non-negative matrices. So I give myself some notation here. So I use this to denote a set of m times p matrices, which are totally non-negative. And you can form a partition of this by defining cells. So each time I'm giving myself a set of minors, okay, I can look at the set of matrices which are totally negative, and for which the minors which are coming from Z are 0, and all of the other ones are non-zero. So I'm kind of fixing the pattern of the 0 minor. Okay, I'm saying every minor coming from Z is 0, every other one is non-zero. So it's very easy to see that these cells form a partition of your space of totally non-negative matrices. One of the issues is that cells might be empty. Okay, and you would like to know whether cells are empty or not. All right, so I gave you an example. So this is clearly a totally non-negative matrix, and it's only zero minor is actually the 2 by 2 determinant, so it belongs to the cell associated to just the determinant here. Okay? Right. So to show you that cells can be empty, let's look at the cell associated to just this minor. So this is a 2-2 entry of a matrix. Okay, so I want just this minor to be 0 and my matrix to be totally non-negative. So I will have a matrix of this form, A, B, C, D, and D will be 0. But D being 0 means, and A, B, C being non-negative, and the determinant being non-negative, forces minus BC to be non-negative. But B and C are non-negative. So this forces BC to be 0, and so B or C is equal to 0. So this D cannot be the only 0 minor in that case. You have to have another one. Hence why this cell is empty. If you want to have 2 in the defining set of the cell, then you need to have as well 1, 2, or 2, 1. Okay. Right. So again, I left you an exercise to do if you're getting bored at that point. You can try to guess the number of possible cells. So there are 5 minors in the 2 by 2 case. So you have 2 to the 5 possible cells, so 32 of them. Actually, only 14 are non-empty. So in general, if you give yourself at random a set of minors, chances are the associated cell will be actually empty. Right. Okay, so good news is that in 2006, Postnikov solved the problem partly solved the problem of describing the non-empty cells. He did that through a combinatorial object called Lie diagram. So what is a Lie diagram? So it's an array of size MP filled in with 0 and 1s. And so this is a non-example. This is an example. What's the difference? The difference is it's a pattern of the 0. So in this one, each time I have a 0, either all the boxes strictly on its left are 0, or everything above, strictly above, is 0. Okay, and you can check that this is true for all of the 0 boxes here, whereas it's not the case for this one. So for instance, if I look at this 0 here, then I have a 1 on its left and a 1 above. Okay, so that's the concept of Lie diagram. I mean, it might look a bit surprising to find this. Actually, it's not. If you follow a bit the arguments I gave you just before, on the slides just before, if you have a 0 entry in a totally non-negative matrix, then everything to its left, sorry, has to be 0, or everything above has to be 0. That's a very easy thing to prove. And that's just a kind of natural pattern that happen in this kind of context. Right, so Postnikov did prove that there is a bijection between the non-empty cells and the Lie diagram of the same size, of course. So each non-empty cell is parameterized by a unique Lie diagram. There is kind of an explicit construction to go from one to the other. One part of the bijection is easier than the other one. I'm not going to insist too much on that. And so for 2 by 2 matrices, this says that there is a bijection between Lie diagrams on a 2 by 2 array and totally negative cells in 2 by 2 matrices. You have 14 of them. So how many diagrams can you form? You can form each box as a 0 or 1. So you have 2 to the 4 possible diagrams, and 14 of them are Lie diagrams. So there are only 2 which are not Lie diagrams. It's very easy to see that this is right. So I have to be a bit careful. No. This one is not a Lie diagram, and this one is not a Lie diagram. I'm getting my zeros and my 1, sorry. Okay, so these 2 are non-Lie diagrams in the 2 by 2 case. Both for the same reason, because of the 0 here and the lack of a 0 either above or on the left. Okay, so we have this nice concept. And it's not exactly what Postnikov did. He did that in a more general context of the grassmannian. So I want to define what the totally non-negative grassmannian is. So you take a point in the grassmannian, and you say this is totally non-negative if it can be represented by a matrix where all the Plucker coordinates are non-negative. That is by k by n matrix, with k being less than n, where all the k by k minors are actually non-negative. Right. So again, you can define the cell decomposition for this by specifying which subset of Plucker coordinates are 0 and which Plucker coordinates are positive. So if you say fix Z, a subset of Plucker coordinates, then you put in this cell all the points in the grassmannian for which the Plucker coordinate coming from Z are 0, and every other Plucker coordinate has to be positive. Right, and again, you should not be surprised to see that there's a bijection between Lie diagrams. It's likely, well, between, I should say, non-empty cells in the totally negative grassmannian and Lie diagrams, this time not on a rectangle, but on all partition that fits into a k times n minus k array. So this is basically coming from the Schubert cell decomposition of the grassmannian. So basically it's saying this is kind of compatible, this theory, with the Schubert cell decomposition, and you can test the total non-negativity of a point in the grassmannian on the Schubert cell side, on the affine side. Right. So I'm not going to insist too much on this, but I'm hopefully giving you an idea of what these objects are. Okay. Right. So why do you care about the totally non-negative grassmannian? Because the combinatorics of this object tend to appear in a lot of different contexts, and maybe some are more surprising than others. For instance, this also allows you to construct soliton solution of the KP equation. So something which is very much in an integrable system. And maybe the most exciting at the moment is it's understanding it will allow you to compute scattering amplitude in the n=4 super-Yang-Ming models. Basically, you integrate forms on an object called the amplitude, and the amplitude is constructed from the totally non-negative cells in the grassmannian. However, to be able to achieve this program, you need to understand better the amplitude, and there are still a lot of conjectures that are that people are trying to prove both on the physics and on the math side on these objects. And a lot of that is, can we cover, for instance, amplitude using cells, totally negative cells in the grassmannian from a certain dimension, etc. Right. So hence why I was interested in this kind of objects, and also because I like this theory. It's quite fun. If you want to explain that to your first-year students, you can discuss this object. So it's not very often I can do that. Right. Okay, so that was a long introduction about total non-negativity, and now I want to move to more the topic of this conference, I guess. So quantum groups. So I will take that on the quantized coordinate ring side. Sorry. So first, let me remind you what a quantum affine space is. So Q will be always non-zero element of my base field. So a uniparameter quantum affine space is just an algebra where you have generators x1, xn, and this type of commutation relation, where M is a skew-symmetric matrix. So nothing too difficult here. So I just gave you an example. If n is 3 and you choose this matrix, it has to be skew-symmetric to make it into a nice domain, etc. Then you get this type of relations. Okay. Right. So that's not very practical. You can't really see what I've written here, but that's okay. So I want to define quantum matrices. So this is a deformation of the coordinate ring of matrices, and you obtain this deformation not at random, but just by asking that this algebra should coact on a quantum plane as the coordinate ring of matrices coact on the coordinate ring of a plane, which is just a polymer algebra in two variables. And if you ask for that, then you obtain these 6 relations. So this is just the definition of 2x2 quantum matrices. Now, there are different ways to define that. So most of the indeterminates Q commutes, but you have this relation here, which makes things a bit more challenging sometimes. And that just shows that this is not quite a quantum affine space, this one. So it is a nice non-commutative polynomial algebra in the sense that it has a PBW basis. So all these monomials in A, B, C, D in this order form a linear basis for this algebra. Okay, so a special element here is a quantum determinant, AD minus QBC, which is a central element. And we've seen this in Kenny's talk yesterday, where he was taking the this minus 1 to form OQ of SL2 or OQ of SU2. So in the case where Q is generic, it is not a root of unity. This is the only central element. Well, if the center is a polymer algebra in this element, otherwise, when Q is a root of unity, you tend to have many more central elements here. Right. So of course you can define larger quantum matrices, and I really need that for this talk. So if you give yourself n rows and n columns, you define your algebra by generators in relation. You have n times n indeterminates that you imagine being on a matrix. And what are the relations? Well, each time you have a sub-matrix of this matrix of generators, you ask for this 6 relation here. So you just need to know the relation for 2x2 matrices, 2x2 quantum matrices to define this one. Right. In the square case where m equals n, you've got a special element which is a quantum determinant. It's just a deformation of the classical determinant, and it's actually a central element again. And what is a quantum minor in this context? This would just be the quantum determinant of a submatrix of this matrix of generator. Okay, so each subalgebra, square subalgebra here is isomorphic to a quantum matrix algebra. You can form its quantum determinant, and that's what I will call the quantum minor. Okay, right. So now I would like to define the quantum grassmannian. So we just naively take the definition of this being the subalgebra of k by n quantum matrices generated by the k by k quantum minors. Okay, so the maximum quantum minors. So here k is less than n, and I will always make this assumption. So I have less rows and columns, and so I'm taking quantum minors from on all the rows and a number of k number of columns. So if you look at the 2 by 4 quantum grassmannian, then you will have 6 quantum minors that generates it, this 6, and they satisfy a number of relations. So most of the time they will Q commute in some way, so like these two. So you can recognize here something which looks like the relation of 2 by 2 quantum matrices. This is no surprise, and you have a Q version of the 3-term Plucker relation here. Okay, so that's the classical one. Okay, so I would like to just give you a bit of an idea of what well, this algebra look like before I go any further. So for this, I need to define a partial order on the set of generators, which are k by k minor. So when I have a k by k minor, I know I'm taking the rows 1 to k, so I will ignore that. But I have to fix which columns I'm picking up to form my quantum minor. So this notation means I'm picking up column I1, I2, Ik. And this is the quantum minors formed on rows 1 to k and columns I1, I2, Ik. And so I can define a partial order on this on the set of generators by just imposing that I1 is less than J1, I2 is less than J2, etc. And that gives me a partial order on my set of quantum Plucker coordinates. Right. So this partial order looks like this in the 3 by 6 case. And what happens is that you can form a linear basis of this algebra. So it's not a non-commutative polynomial algebra. It does not have a nice PBW basis, but you still have a linear basis, which is kind of nice, which is form of monomials of elements which are comparable in this ordering. So here, for instance, you have this standard path, and that leads me to a first set of standard monomials in this quantum minors. Of course, you have to look at all paths, and from all the families you can take, like you can form like this to get a basis for this algebra. So you should ask yourself, what that means. If this is a basis, I should be able to rewrite the product of these two non-comparable quantum minor, quantum Plucker coordinate in this basis. Actually, you can use here a three-term quantum Plucker relation to actually do that. And if you write the quantum Plucker relation, this product up to scalars will be equal to the product of these two, which are comparable, plus the product of these two, the two green ones, which are also comparable. So that's how, using the quantum Plucker relations, you can actually obtain this structure of quantum algebra with a straightening law, I call that. Okay, right. So this is a slide where I start making the link between the totally non-negative side and the quantum side. So what we did prove with Lenegan and Nolan a few years ago is is the following. So take a family of Plucker coordinates, F, and take FQ to be the corresponding family of quantum Plucker coordinates. Then the following are equivalent. The totally non-negative cell associated to my classical family is non-empty. And the corresponding quantum family is a set of all the quantum minors that belong to a prime ideal in the quantum grassmannian. Okay, well, so here I'm assuming Q is not a root of unity. Right, so it's even better if I assume that Q is transcendental. Let's see. I don't have to, because if you're not homogeneous, and you contain a Plucker coordinate, you will have to, this Plucker coordinate will have to be in the homogeneous prime inside the prime you're considering. Okay, so that does not change the families. Right. So, okay, I need to press harder or lighter. Okay. Okay, I think this pointer does not like mornings. Right. Okay. Right. So these families of Plucker coordinates in the classical case, it's just me. Yeah. Should have done a board talk. All this technology, it's these families of cells which are non-empty define the so-called positroid varieties. So you can look at the zeros of this, and that will form what's called the positroid varieties. And that's what physicists want really to understand. So as a variety, they are very nice. They are reducible. There are plenty of things we know about them. Right. And when Q is transcendental, these families FQ generate a completely prime ideal. And this quotient will provide actually a deformation of this positroid variety. So that's a corollary of this result, an easy corollary actually. So this is quite an interesting object to consider, because there are plenty of things that maybe you don't see in the commutative setting here that you can try to compute. So attached to this, well, I have a family of algebras I can study, and you can look at invariance for positroid varieties by looking at invariance for these quantum algebras. Since they are living in a non-quantitative world, there are things that maybe you will not see very easily otherwise. So what I would like to do today is try to compute the PI degree basically of these algebras in the case where Q is not a root affinity. Why? Because it will give me some invariance for the positroid varieties that I could not see necessarily in the classical setting. My hope was that by controlling the PI degrees and sorting out some combinatorics, I could actually solve some of the physicist questions, but I'm probably a bit too far away from that just because I can't compute all the invariants in that case, but I will try to explain where we are with this. But that's the idea, is we have a nice deformation of the positroid variety, and then try to compute invariance on the quantum side to try to sort out your problems on the classical side. Okay, right. So I can't take any at the moment. We can't do that we can't compute the PI degree for every quantum positroid variety, but we can try to do that for quantum Schubert varieties, which is a first approximation to the problem. So what is a quantum Schubert variety? So you fix yourself a Plucker coordinate, let's say this one, and you can form an ideal generated by some Plucker coordinates, namely all the Plucker coordinates which are not bigger than or equal to this one. Okay, not bigger than or equal to this one. So you can see that it contains all of this one because they are smaller, and these two because they are not comparable. Okay, so that's the Schubert ideal associated to 1, 3, 5. And then you can look at the quotient, and it's a nice algebra because you can see again, I have a nice poset that looks like the previous one, and so I inherit the structure of a quantum algebra with a straightening law, so I have a nice linear basis for this quotient algebra as well. Okay, so let me be a bit more specific. So I fix gamma to be a quantum Plucker coordinate. I can define the corresponding quantum Plucker ideal, which is ideal by I gamma. So this is generated by all the Plucker coordinates which are not bigger than or equal to the one I fixed. And there is a nice way to relate the quantum grassmannian side with kind of affine side. So everything here, you have to think this is projective geometry, and you want to affinize that to make it easier for you. And it turns out you have this non-commutative dehomogenization that tells you that if you look at this quotient, then this element gamma, its coset becomes normal in this quotient. I've broken it again. Okay. It becomes normal here, so I can localize. And it will be isomorphic to a skew-Laurent extension of an algebra A lambda. And what is this A lambda? This is actually just a subalgebra of a quantum matrix algebra. And this is generated by the generator of this algebra, which fits into a certain partition. So I don't want to explain that in words. I will explain that just with a diagram. It's easier, I think. And we control, of course, what the automorphism sigma lambda is. It's just multiplying each generator by Q. So this is what I will call the partition subalgebra or quantum Schubert cell. Right. So let me just show you on an example what this partition subalgebra is. So if you take this cell associated to 1, 3, 5, so starting from the north east, going to the southwest, you can draw a Young tableau by using 1, 3, 5 as your descent and missing numbers as your step going to the left. So 1, 2, 3, 4, 5, 6. And A lambda would be actually, in that case, a subalgebra of supersymmetric quantum matrices generated by x11, x12, x13, x21, x22, x31. Okay, so indeterminates generating quantum matrices that fits into this Young tableau. You should think, if you think my construction looks strange, it's what you do when you do row reducible form and you do the Schubert cell decomposition of the grassmannian. So it's nothing different actually. If you think about that, if you have a matrix and you're saying, I want the minor, you have a 3 by 6 matrix, and you want the minor 1, 3, 5 to be non-zero and actually equal to 1. So you're putting your row reducible form will have this form here with that should be a 0, sorry. You will have your ones here in columns 1, 3, 5. And if this is a row reduced echelon form matrix, then you have zeros everywhere apart from the boxes where I have stars. And you can see the Young tableau pattern here appearing in that context. So it's just a quantum version of the Schubert cell decomposition. Right. So at that point, I should say that depending on the value of Q, you have a dichotomy for what happens. So in the case where Q is not a root of unity, your algebra, your quantum grassmannian, for instance, is an algebra with a very small center, or quantum matrices is an algebra with a very small center. In the case where Q is a primitive root of unity, in that case, the center becomes huge, and your algebra becomes finite dimensional over its center. So if you look at 2 by 2 quantum matrices, not only the quantum determinant is central, but also all of this indeterminates to the L. And because this is an algebra which is finite dimensional over its center, it becomes a polynomial identity ring. And you can try to compute a lot of things for this algebra. I mean, this is Noetherian prime PI ring. So there's a lot of things that have been done in the 60s, 70s on this algebra. Right. So I will focus on that case from now on. And I want to compute the so-called PI degree. So let me remind you what this means. So what is a PI ring? So polynomial identity is just non-zero monic polynomial with integer coefficient in non-commutative indeterminates, and a ring is PI if you can find a polynomial identity, if you can find such a polynomial identity that is satisfied for any tuple of elements of your ring. Okay. Right. So if you think about that, it looks like a strong ask, but actually any commutative ring satisfies this monic identity. So this was a way to try to generalize commutative rings. And of course, the degree of this identity is 2. And so one thing that you are interested in is that in the case you have a PI ring is its minimal degree, that is the lowest degree of an identity that your ring satisfies. And the PI degree, when you have a prime PI algebra, is defined as half of this minimal degree. And it plays a very important role in a representation theory, this PI degree. Why is that? Because it gives you an upper bound for the dimension of the irreducible representation of your algebra. So in that case, all irreducible representation will be finite dimensional. We are quite far of the cases we were discussing yesterday in Robert's talk. And if you can compute this PI degree, that will give you an upper bound. So that's a very nice way to try to construct, to see where the irreducible representations are, because you won't have to go too far. Right. So what I would like to do is start by trying to compute the PI degree of this partition of the subalgebra. So subalgebra of quantum matrices generated where the generators fits in a Young tableau. So there is a result of NL that allows us to do that, because this algebra A lambda can be presented as an OR extension, iterated OR extension. And when you're in a case like this, I can't read anything from there. So where you have automorphism and skew derivation, and Q is not a rate of unity, then the PI degree actually of your algebra does not depend on the skew derivation at all. So you can forget about that. And because all your automorphism sends a generator to a Q multiple of another of the same generator, then you just get a quantum affine space for what remains when you just have the automorphism. So basically it says you can forget the skew derivation and everything will be fine. So you're left with computing the PI degree of a quantum affine space. And for that, the Concini and Procesi have a general result that tells you how to do that. And this says that if you want to compute the pi degree, you should look at the square root of h, where h is the cardinality of this map. So what is the map? So you have this Q-symmetric matrix that define your quantum affine space. You can, so you first apply lambda, and then you're projecting your result on modulo L. And so now the image of this map will be finite because I have a finite set here. And you want to compute the cardinality of this image. And square root will give you the pi degree of your quantum affine space. Right. So the good thing about that is that it tells you exactly what you need to do to compute the pi degree of a quantum affine space. Now, if you remember a bit of your linear algebra courses, every skew-symmetric integral matrix is congruent to a matrix, a diagonal matrix of this form, where on the diagonal you have 2x2 blocks of this form, where hi are integers, and they are, well, you can always assume they are positive, and these are the so-called invariant factors of your algebra. And interestingly, when you have two matrices which are congruent, the pi degree can't change. I mean, because if the two matrices are congruent, then their quantum torus and quantum affine spaces are isomorphic, which means that the pi degree are the same. So the cardinality of the map won't change. And instead of using the lambda, it's easier to use something like this. I mean, computing the image in that case is becoming very easy, because you're sending, in that case, you will be sending the first, you will send the first canonical vector of Zn to what, minus h1 e2, I guess, and then you're projecting mod L, so minus h1 bar e2. And it's not very easy in that case it's not very hard in that case to compute actually the image. It will be related to the fact that whether this is 0 or not, for instance, modulo L. There's a bit of arithmetic to be done, but it's nothing difficult at that point. Right, so let's try to compute this pi degree. So first I use NL theorems to say this is a pi degree of a quantum affine space. And well, the automorphisms that define the quantum affine space are those ones. You won't like this definition, so I will skip very quickly and just say, okay, how do I form the matrix how do I construct the matrix that controls the Q commutation relation for my partition subalgebra, just by thinking of two indeterminates. If they are let's say here and here, they are not in the same column nor in the same row. And so I mean, so this in this case here, so the commutation relation between these two entries has to be a 0 if my square I is strictly below or strictly if square I is strictly below or strictly below and left probably of square j. Sorry, there's left is missing in the first sentence. Right. So you can look at these two indeterminates. How do they commute? They Q-commute because they are in the same column, basically, etc., etc. So this is an easy way to control the commutation relation. And basically, NL theorems tells us that we have to compute the pi degree of the quantum affine space associated to this matrix M lambda. Right. Okay, so that's what the summary of what I just said. And if you're interested in looking at the quantum Schubert variety here, then you can use the homogenization to say to use the same thing to say, oh, it will be the same as the pi degree of a quantum affine space, but this time the matrix is the same as the one I've just defined, augmented by a column of 1 and a row of -1 with a 0 in the last entry. Okay, so I am left with computing the invariant factors of this matrix and the M lambda matrix. Okay, so that's where we could find something interesting. All the invariant factors of M lambda, I'm not computing them, but we can prove that they are all powers of 2. So each time you will have your L, which is odd, it will be co-prime with all the invariant factors. And in this case, this or 1 will not change anything. So you know exactly what the image of your, the size of your image of your map will be. For the augmented matrix, well, most of them will be powers of 2, except possibly 1. And this one is a bit of a pain because you can have invariant factor for that matrix which are not powers of 2. But the odd prime factors are always bounded by k and n. So that depends very much on the size of your quantum grassmannian. Okay, so we control basically everything here. The only thing we are not controlling in this map is the size of the kernel of this map. Okay, because I want to know what the kernel is. And to control the kernel, we can proceed as follows. So let's start with the Young tableau here, which corresponds to the matrix M lambda, or the partition sum algebra associated lambda. So I will complete it into a rectangle in this way by putting black boxes here. And each time you have a diagram, by which I mean a rectangle with white and black boxes, you can do a so-called pipe dreams construction as follows. So first number the side of your diagram as I did it. So 1, 2, 3 from bottom to top, and then 4 to 8 from left to right. And in each box, I will replace, when I see a white box, I will put a pair of elbows, oriented elbows like this. And when I have a black box, I will replace it by a pair, well, by a cross like this, an oriented cross. And this gives me a permutation by just following the pipes. Okay, so to each diagram like this, I do the pipe dreams construction, and now I have a permutation. 1 will be sent to 7 for this construction, 7 will be sent to 1, 2 will be sent to 6, which will be sent to 3, etc. Okay, so each diagram like this, through this construction, gives you a permutation. And interestingly, this permutation gives you the number of, I choose D, but actually I should have said, lambda. So gives you the dimension of the kernel of the matrix we are considering. Why? This is equal to the number of odd cycles in the disjoint cycle decomposition of the permutation I've constructed. And in the case where Y lambda is just a partition, then we can actually explicitly compute this permutation. It's a product of 3 permutations. So you can see the longest element in Val group, the longest element for the stabilizer of Sm times Sn, and then the permutation W lambda corresponds to this permutation here in one-line notation. So we know exactly which permutation we have to deal with. And so we know the dimension of the kernel. We know that the invariant factors are powers of 2 up to 1 of them. And that allows us to actually compute explicitly the PI degree of the partition subalgebra and say this is L to the n minus R over 2. So the over 2 is because we are taking the square root of the cardinality of the image, and n minus R is basically the rank of your matrix. R is being the number of odd cycles, so that's just the dimension of the kernel. So that's basically the rank, and because all of these invariant factors are actually coprime with L, we can make them disappear basically when computing the cardinality, and so every possible vectors will appear in the image. So that's a nice formula, quite easy. And so you can actually really do explicit computation with that by just well, take a partition and take an L and try to compute explicitly what it is. And we also developed algorithmic method to produce irreducible representation of that dimension. So something that you want to do, you want to compute the pi degree, but make sure that you can construct at least one representation of that dimension. Okay, and what about quantum Schubert varieties? So in the grassmannian case, so it's not as pretty because of this final invariant factors that we don't really control, or not as much as we would like. So what we can say is, so the effect of adding this column of 1 and this row of -1 is it will make things change by a +1 potentially. And it depends very much whether the kernel of your static matrix, your affine matrix, is contained in the orthogonal of the vectors with just ones. If this is the case, then the pi degree doesn't change. If not, then it's increasing by a factor of L. And that's something that, I mean, there are cases where this happens, there are cases where it doesn't happen. What we don't know is whether we can decide just by looking at lambda whether this condition is satisfied or not. In the case where lambda is n, then we can actually, well, we have a condition for this to happen explicitly, but it's not known in general. Okay, but the conclusion is that we can compute the pi degree in this quantum for this quantum Schubert varieties. It would be interesting to be able to do the same computation for quantum positroid varieties because it will give you invariance for your classical positroid varieties. But that seems to be the next step. Okay, I will stop here. Thank you. Bien.